ProMax Sulfur Recovery with Kinetics webinar. We're going to talk about some of the new kinetic modeling features available for Sulfur Recovery Units and ProMax 6.0. My name is Zach Allgaier. I am one of the technical support engineers here at Bryan Research and Engineering. I have been here for, going on about 5 years now. This webinar, we are going to probably spend 40-ish minutes with me talking about all the different features available, what they mean for you, and how they can be useful for users as well. And at the end, we are going to open it up to questions. So during this talk, I'm not going to be answering questions or looking at the chat. We're going to save that for after my presentation. This also will be recorded and will be released later. So if you ever want to rewatch it or tell your friends that I was such a great presenter and maybe make me a little YouTube famous, then that is available for you to do as well. But enough show gloating for me. We're going to start talking about the SRUs in general, the ProMax, the new ProMax kinetic modeling that is available for us. And to get into it, we're going to look at an agenda quickly. Our agenda is going to work by just kind of going down the line of some of the things that are available for us in ProMax. We're going to look at the reaction furnace and Klaus beds. We're going to just talk about the new things that are happening there, the new reaction sets available for you, as well as some new flow sheet drawing that we may need to do as well, depending on what you are modeling. We're also going to talk about modeling Klaus bed pressure drop. So no longer are we are able to now use some bed information to calculate expected pressure drops along a bed. The pressure drop specification is still there for you, but this is a new feature for us. We are also able to simulate Klaus bed catalyst activity. There is a tuning parameter in the Klaus bed reaction parameters that we will talk about, as well as a few other things there too, for better tuning your models for matching your catalyst activity. Previously in ProMax, and still currently, we have been using Gibbs minimization reaction sets. Gibbs minimization reaction sets, they work by finding an equilibrium between your inlet and outlet and then determining reaction paths by minimizing Gibbs free energy. These Gibbs minimization sets, if you've ever been to, say, a ProMax training, you may be familiar with it. If you ever modeled SRUs in the past as well, you would use Gibbs minimization Gibbs sets to model various things, whether it be your acid gas burner, your Klaus bed, that sort of thing. And in the screenshot here, we can see that we are modeling just that in a reaction furnace, an acid gas burner using a Gibbs minimization type. New to ProMax 6.0, we do have some kinetic reactions available for our SRUs. Now, some of the different reaction sets that are available, we've talked about things like the Gibbs minimization. We've talked about how there are reaction sets. You may have seen that on your own with some ProMax work in the past. With ProMax 5.0, we've always had reaction sets. That's where you would write your own reaction. With these kinetic reactions for SRUs, for the burner and the Klaus beds, we're treating it where you do not have to write your own reactions here. We've taken care of that for you. We've taken care of the reaction parameters for you as the user. The only thing that you would use is actually the built-in reaction sets. And if you look on the screen, there is a screen grab where we are working with a plug flow reactor type. So we're no longer working with Gibbs. We're mainly going to be working with a plug flow reactor type. And our built-in reaction set will be a Klaus furnace anoxic zone. So that'll be modeling the anoxic zone of the Klaus furnace. Specifically what that is we'll talk about that in just a second, but this is just a quick screen cap demonstration of how it'll look a little different for you, the user, and the user interface. Now, why do we want to use the kinetics? Why is this such a big deal? Well, the kinetics can help us better understand, better represent, better model individual reaction paths along your reactors. With that comes more fine-tuning. There are a lot more tools available for you now to manage intermediate steps or manipulate them as well. And this can help you with making your plants model more towards reality, or the expected reported behavior of your plants. You can go into several different things, several like absorption, desorption steps as well in the Klaus bed. You can modify those. So the kinetics, it's not the equilibrium pathway anymore. We do have this reaction pathway that we can now model, and we can now manipulate and fine tune to be more representative for you and help the user understand more of what's really going on in their SRU process. Now that we've talked a little bit about what exactly we're doing and why this is all important and such, let's talk a bit about different blocks available. So we have the reaction furnace. That is one of the things available for us in ProMax now kinetically. Now the reaction furnace, we are going to model it with two blocks. We have a flame block and we have a block for the chamber as well. They'll use a flame zone and an anoxic zone built-in reaction set respectively. Now we are going to be modeling two different parts of the burner. So if you look on the PowerPoint and you look at the beautiful picture that is presented here, we do have what is a picture of a SRU reaction furnace with a waste heat boiler attached offline, just sitting in a field somewhere. Toward the right, all this gray here, all this dark gray matted looking material. This is the waste heat boiler with a steam drum attached, but really what I'm talking about here is this more shiny, larger vessel. This more shiny, larger vessel, this is going to be where the burner and combustion chamber is. This is really what we're looking at here. And like I said, we're going to have to model this with two different blocks. We will have a block representing just the flame zone and one for the chamber, which will use an anoxic zone reaction set. When we model the furnace, where my arrow is pointing, we're modeling the flame zone. We'll use a Klaus furnace flame zone Gibbs set, so we're still using a Gibbs set in this case. And the flame is going to be modeled sort of where the red arrow is. So that red arrow on the silver pipe that's going into the main chamber, that is approximately where the flame for the SRU burner is going to be. So we'll have a block modeling that part of the vessel. And then next we'll have the reaction furnace chamber itself. That chamber will use a Klaus furnace anoxic zone built-in reaction set. It's called the anoxic zone because this is post-combustion, so we don't have any more oxygen in the system available for combustion, hence the name anoxic zone. The red arrow pointing out to that chamber is representing the block that we are going to be modeling. So we have an anoxic zone block. We are looking more towards that chamber itself. When we are modeling the chamber is going to model that the combusted gases leaving the flame zone are going to mix and react with each other. We're assuming that there is ideal mixing occurring. Like I mentioned before, we are using the Klaus furnace anoxic zone. Again, to repeat, the anoxic zone is just saying that we are at a point where we are no longer using oxygen for the combustion. We are in a post-oxygen state, post-oxygen zone. We're using this as a plug flow reactor type, and this is going to be a kinetic reactor. Now with the plug flow reactor type, this is a volume-based kinetic reaction set that we are using. With it being volume-based, we suddenly become very interested in, well, the volume of the vessel. The volume of the vessel helps us determine residence time of our reaction to determine how far along our reaction will go. In order to figure out the residence time, we will need that volume. In order to figure out the volume of our reactor, we are going to need to put in some hardware information. Hardware information that we can put in, we would want to put in a length and diameter. So if you look at my screen, there is a screen grab showing the hardware section under the process data of our anoxic zone. We will put in a length and diameter, a rough length and diameter of our anoxic zone of our chamber. We're going to be modeling this chamber as roughly a cylinder. So there are a couple more things we'll need to put in, a tube count and a count for how many passes that we're seeing. Since we're modeling this chamber, this anoxic zone, as a cylinder, we're just going to count the whole cylinder as one big tube. So we'll have our tube count as 1, and we're having 1 pass specified. We're not having our gases go through the chamber, back to the burner, through the chamber, like a alternating current or a multi-pass heat exchanger or anything like that. We're just going to have our gases go from flame to the tube sheet before the waste heat boiler. What I'll do now, though, is I will go over to the ProMax side of things. So I do have a ProMax model available for us, and I'm going to go in and show you how we can do some modeling with this. So first what we're going to do is we're going to go over to the flame zone. Remember, the flame zone is where the flame is happening. This is going to be a Gibbs set reaction. We're assuming that there is instantaneous combustion. Right where that spark of ignition happens, we're saying there's the reaction. It happens right there. It's very instantaneous. And that's going to be at that front end in that smaller silverish pipe, if we remember from our picture, entering the large chamber. We'll double click on the flame zone. Go to the process data tab, and under specifications, we'll make sure that we choose the Gibbs minimization type reactor. And then from the Gibbs set, we will choose the Klaus furnace flame zone. So chose the Klaus furnace flame zone. I'll put a pressure drop, something small, about 0.5 psi. We do need to put a pressure drop in for ProMax blocks. I'll exit out of the project viewer, and I'll click on execute flow sheet and let the flame zone turn green. One thing that you see is that after the flame zone, we do have a property call out displaying the COS and CS2 content in the post flame zone exhaust gases. So before the anoxic zone, right after the flame zone, right after combustion reaction, we are going to see some CS2 formation. We're going to get that CS2 from the hydrocarbons interacting with some of the sulfur species coming in, or excuse me, being formed from the H2S combustion and Claus reaction. We do assume overall that all of our hydrocarbons will go to completion except for one group, and let's talk about that real quick too. We go into the flame zone. We are going to look at the constraints. Under the constraints tab, this is where we take into consideration some of the kinetically limited components within the flame zone. So for our Klaus furnace, we already have a kinetic limitation for the CS2, and we do get constraints from data from like ASRL and NSYNC, and that tells us, based on certain parameters, how much formation or destruction of certain components that we're going to see. By default, we do have a CS2 constraint that comes in, but if you had something like benzene in your feed, that can occur. Benzene is a kinetically limited component. It's not going to fully destruct like the other components, like the other hydrocarbons, as readily. So what we would do is to add that constraint, we would click on Add at the top. We would choose this Klaus furnace flame zone constraint. Click OK. Once we've done that, we'll go to the component cell for our second constraint, and we would choose the benzene that is in our feed. I'll select the active checkbox to activate this constraint. And then from there, I would re-execute the flame zone block. Moving on though to the anoxic zone. So we modeled the flame zone, we modeled the flame occurring. We can now go to the chamber. So the anoxic zone is going to be our chamber of the furnace. If you remember that large, more or less shiny steel chamber, that's going to be our anoxic zone. To specify the anoxic zone, we'll double click on that as well. The reactor type is going to be a plug flow this time. It's not going to be a Gibbs set, it's going to be a plug flow. And then when we do that, we have a built-in reaction set available for us to choose from now. And we have a few available, but we're going to choose the Klaus furnace anoxic zone. Once I've chosen the Klaus furnace anoxic zone, I have to put in a pressure drop of 0.5, something small. I'm just using 0.5 for demonstration purposes. The next thing that we'll do is we'll go to the hardware tab. In the presentation, I talked about us needing to put in some hardware information. The hardware information allows a volume internally to be calculated and will be displayed on the flow sheet with the help of a specifier, but that'll also help determine the residence time so we can figure out just how far this reaction really goes. And then the residence time will also be displayed on the flow sheet. We'll see in just a sec with the help of specifiers and stencils. So we go to the hardware tab. The first thing I'll do is just put in our tube count and passes. We're modeling this anoxic zone as one large cylinder. We're going to treat the entirety of the chamber as one tube. So that'll be a tube count of 1. Then we'll have 1 pass. Again, remember, we do not want to model that our gases are being sent back and forth like maybe a multi-pass exchanger or something like that. We are just having our gases go from flame to tube sheet of the waste heat boiler. From there, we'll put a length and an outside diameter. And for demonstration purposes, I'll say that we have a length of about 4 feet and outside diameter of 2.5 feet. When I do that, I'll click the exit button to leave the project viewer, and then I'll execute the flow sheet from there. And then once everything is turned green, we can see some information about some of our new COS formation as CS2 has destructed. The anoxic zone is also where we would see the ammonia destruction occur as well for if you had ammonia in your feed from a sour water stripper or other sources. Below, you'll also see that we have a stencil with the help of simple specifiers displaying the furnace volume and the residence time of our gases based off the inlet feed. So right now, our furnace residence time is about 2 seconds, a little over maybe, and we generally recommend that residence times for the anoxic zone be about 1/2 to 2 seconds. Okay. So now that we've done the flame zone and a noxic zone, we can keep moving on. I'm going to go back to the PowerPoint now. And we're going to start looking at Klaus beds. Klaus beds also now have the reaction kinetics available. Looking at specifically the titanium and alumina beds, we can model both. They do each have the same, maybe we shouldn't say same, but they have the Claus reaction, the COS-CS2 hydrolysis, the sulfur redistribution reactions as their global reactions in both sets. I caught myself when saying the same because that's not entirely true. The titanium and alumina do have different kinetic parameters. So even though you were to draw out or write down stoichiometrically the different reactions, they may look the same, but all the data that's within the blocks themselves are going to be different. They'll be looking at different kinetic parameters and make different calculations based off of that. I do want to note, though, that the catalysts that we are going to model are just going to be the nominal behavior for standard titanium and standard activated alumina catalysts. Our Klaus beds do use plug flow reactor types. And like I said, we are going to use an alumina or titanium catalyst. These conversions are going to be these conversion reactions are going to be built-in reaction sets available for you. Again, you don't have to write anything as the user. You can just use the ProMax available built-in reaction sets. And you can see in the screen grab below that we are modeling a Claus converter using an alumina catalyst based off of the built-in reaction set that is chosen. One thing I want to talk about too is specifying your catalyst. But then once we've done that, we'll look at ProMax again, but let's talk about specifying the catalyst real quick. So with the Klaus beds, whenever we are modeling them, we do need to at least specify the amount of catalyst that is being used. We want to specify the mass of catalyst minimally that is being used, and that is because the kinetics are going to be on a moles of gas per mass catalyst basis. What I mean by that is the data that we have says that our gas will come in at certain conditions, and based on those conditions and the amount of either titanium or alumina catalyst available, based on the mass of catalyst, we're going to see a certain amount of conversion. Okay, so on a moles of gas per mass of catalyst available, we're just saying with how much gas and their conditions coming in, based off how much catalyst we have, again, we will see a specific amount of conversion occur. Now, if you have a Klaus bed that is two different catalysts in the real world, say like your first bed typically, where there is an alumina bed and a titanium bed for the or specialized COS-CS2 hydrolysis, and ProMax will need to model that as two separate blocks. We'll have to split up the beds, so we'll have a first Klaus bed as an alumina section, and then we'll have a first Klaus bed as the titanium section, as you can see in the screen grab to the right of the PowerPoint. Did it like this in this drawing because typically it's the alumina then the titanium. The alumina conversion that occurs for the first bed feed helps heat everything up. You know, this is a exothermic reaction, right? These Klaus conversion reactions are exothermic, so the more conversion that happens, the hotter the environment should get. And the hotter the environment gets will actually help with COS and CS2 hydrolysis. So we use this alumina to heat up the environment, and then we send our gases to the titanium section, where hopefully it's hot enough to be able to do some COS and CS2 hydrolysis. But like I said, when you model things this way, you're going to need to model them with their own respective bed. And we're going to go ahead and do that right now. So let me escape and go to our ProMax model. What we'll do here is we're going to go to the first Klaus bed, the alumina. I'll double click on that. Under the process data tab and specifications, similar to the noxic zone, we are in the same spot, but we're going to make some different specifications. The type of reactor is going to be the plug flow reactor. And then our built-in reaction set, since we are on a Klaus bed with an alumina bed, we're going to use the Klaus converter alumina built-in reaction set. Now I'll put another small pressure drop, say about 0.5 psi. And then lastly, what we'll have to do is we have to go to the hardware tab. And here we'll have to put in a total catalyst mass. So total catalyst mass, we'll just say it's 1,000 pounds of alumina for now, for demonstration purposes. So we're saying that in this bed there's 1,000 pounds of alumina. I'll exit out of this project viewer and then go ahead and repeat the process in the first Klaus bed. So I'll double click on the Klaus bed for the titania, go to the reaction type and select the plug flow reaction type. Under the built-in reaction set, we'll use the Klaus converter titania. And a small pressure drop too. And we'll go over to the hardware. Every time that you choose the Klaus converter type, ProMax will automatically know that by default we want to at least specify the total catalyst mass. We'll talk about more things that you can specify in just a second, but like I said, we will do total catalyst mass for now. We're going to say that the titania amount is about 2,500 pounds. Demonstration purposes, so we have 1,000 pounds of alumina and 2,500 pounds of total mass, total titanium mass, excuse me. And then from there we will go ahead and execute the flow sheet. And then once all of that is green and solved, we are so far good to go. One thing I want to talk about too real quick with this Klaus bed is that we looked at the specifications and hardware tabs. There's also a components tab where you can see individual component conversions. So you can see things like our H2S conversion with sulfur production. So those negative conversions means that they are being created. And another thing I would like to look at too is this reactions tab. So under the reaction tab, you can see the extent that the reaction occurs, pound mold per hour. And you can also see which reactions are being represented from the built-in reaction set. So like we mentioned in the PowerPoint, we do have a Klaus reaction with our CS2 and COS hydrolyses, and then the different sulfur species redistribution equilibriums. So this is another great way how the kinetics can help you as the user understand the more intricacies of what's going on in your Klaus bed or your noxic zone. We are able to display these specific reactions. We're going to go back over to the PowerPoint now. We're going to talk further about the Klaus bed. So we talked about just setting it up. We talked about using the masses as the minimum specification for figuring out our overall conversions. But another thing that is available for us is that Klaus bed pressure drops can be calculated. As you've been watching me throughout this presentation, you've seen that I have gone through and made specifications for small pressure drops like that 0.5 psi that I've been doing. Based off of bed information, like its diameter, length, void fraction, things we'll talk about in just a second, ProMax can go ahead and make pressure drop specifications for you. The pressure drop specification, the pressure drop calculations we made off of some correlations that are available for these single pass beds, these not single pass, excuse me, these single phase beds. And the pressure drop correlation, like I said, there are many to choose from, but they do correspond to the Reynolds number that is calculated. Okay, so below I've grabbed this picture just from our ProMax help, and there are several different pressure drop correlations available with their suggested ranges of validity based off of the Reynolds number. Typically, we do fall in the ergon pressure drop correlation. That's typically where this will fall under. I have seen some rare instances where it does fall outside of that. If you use a pressure drop method that has a Reynolds number outside of its range, you will get a warning from ProMax just letting you know. But by default, I do like to start with the ergon pressure drop correlation, and we'll talk about how to specify all of that in just a second. Looking down, we do have some specifications that we'll need in order to get to our pressure drop calculations. In order for ProMax to go in and calculate expected pressure drop for us. So we've already put in a total catalyst mass. Next thing that we'll need to specify is a particle diameter, so the diameter of your catalysts. The length and diameter of your Klaus bed, so how deep it goes and what its bed diameter is. Now I understand that a lot of these Klaus beds are not a perfect cylinder. They may look a little oblong, maybe a little more oval if you're looking at it from a bird's eye view. And what we recommend here is just finding a diameter that would give you an equivalent surface area. Next thing we would mention as well as the tube count and passes. We're going to treat the reactor itself as just a wide open cylinder, akin to what we did with the anoxic zone. So we're going to say that the reactor itself is the tube. So there's only going to be one tube. And the gases are just going to go straight through. There's not going to be any reverberation, any back and forth. So it will be our one pass. We also will need to put in some void fraction information. The void fraction, the space open available within the bed for the gas to pass through, the space that's not taken up by the solid catalyst particles. All these things are going to go into an equation that's going to calculate for us a friction factor that will then go into a pressure drop correlation available too. All these things are in the ProMax help, the friction factor and the pressure drop equation. They are all going to be the same for each correlation that we use. The only difference is that these A, B constants will change depending on which correlation you're using. Then the Reynolds number can also change just depending on what the size of your reactor is, flows, viscosities, all that sort of information. But like I said, the pressure drop equation, that we use to determine your pressure drop, as well as the friction factor that goes into it, it's going to be the same for each correlation. It's just what numbers are you going to be plugging in. So let's go ahead and work on that too. I'll go back to ProMax. I'll exit out of this project viewer we were just looking at. And this time we're going to go pick on the second Klaus bed. So let's double click on the Klaus bed, the second Klaus bed. Then under the project viewer, see that we are on a type conversion. So I'll change this over to the plug flow and make sure that we are also looking at an alumina converter. We have a pressure drop cell available for us, and then there is also a pressure drop correlation cell right below it. By default, it says use your input, meaning the pressure drop is going to be whatever the user inputs into ProMax. We could choose a different pressure drop correlation from the ones that I have displayed in the PowerPoint, but we're going to choose ergon as our default option. Generally, ergon works. If your Reynolds number is outside that range, ProMax will give you a warning saying so, and then you can choose a different pressure drop correlation that fits that range better. But usually, ergon will work for you. So I'll choose ergon as our pressure drop correlation. Our ergon parameters 1 and 2, those A and B's from our ProMax help table that I copied and pasted into our PowerPoint are now available to see. We go over to our hardware tab. The first thing that I'll put in is a total catalyst mass of 2,000 pounds. We'll also have a particle diameter of 0.25 inches. Have a tube count of 1 and a pass of 1. Next thing we'll look at as well is our length of bed and our outside diameter. So we could say that the length would be like 3 feet, and the outside diameter, we'll say for demonstration purposes, it's 4.5 feet. These Klaus bed sections tend to be wider than they are tall, more pancake than hot dog. And then below we'll also put in a void fraction. In this case, we're going to say that the void fraction is about 35%. We'll close out. Then I'll execute the flow sheet while I zoom out a little bit. And then once the flow sheet is done calculating, everything is turned green, we are solved. We can see at the bottom that we do have a couple of call-outs for us as well. We have a second Klaus bed Reynolds number being calculated by help of a specifier being displayed with a property stencil. Klaus bed being 167 Reynolds number, which is more than okay for our ergon pressure drop correlation. And then based off of all the information that we have as well, we can figure out the second Klaus bed space velocity, of about 1,329 1/hours, which is the inverse of the resonance time. And not like I'm trying to show off any quick math or anything. I did do the calculation before this presentation, and this would turn into a resonance time of roughly 2.5 seconds. If I double click on the Klaus bed as well and go to the specifications tab, we can see that we have a pressure drop specified. In this case, it's a small pressure drop of about 0.11 psi. So in this demonstrative purpose, we have a small pressure drop 0.11 specified based off of our different hardware specifications. I'll exit out that project viewer and we'll go back to our presentation. There's one more thing we should talk about, and that is going to be the Klaus bed activity. So our Klaus bed reactions, we can now demonstrate the activity of your catalyst. By doing so, we use the reaction activity that is under the parameters tab of your process data tab in your Klaus bed. If you remember, we did look at hardware tab, reactions tab, and to the furthest right there is a parameters tab with some more information, which we'll talk about in a second. But at the bottom left of the window of the screen grab that you see on the PowerPoint, there is an activity. Activity, like I mentioned, represents the activity of the catalysts. An activity of 1 represents a fully active catalyst. If you have an activity less than 1, that's going to model some catalyst deactivation. As catalyst deactivate, then that means that there's going to be less reaction occurring. There's less reaction occurring, less conversion occurring in the Klaus bed. that's less of an exothermic reaction occurring. So that means that the temperature difference between the inlet and outlet will not be as great as with a fresh catalyst. So the outlet temperature may start to look like it decreases over time if you're not compensating for that by increasing your reheater as time goes on. You can use a solver on your activity to solve for an outlet temperature. And that can help you simulate and match your catalyst activity based off of the known temperature parameters that you have around your facility. In the screen grab on the PowerPoint, you can see that the activity cell shaded in blue. If you've been to a ProMax training before, you know that that means that that value is coming from some calculator that the user has created, in this case a solver, and the activity is about 0.65. So what that means is that we are seeing that 65% of active sites on the catalyst are available, or an equivalence like that. While this could model a deactivation, there is an equivalent that it can model as well, whether it be like the sulfur condensing onto the catalyst and then just blocking some of the catalyst pores. Or maybe there's channeling occurring as well within the catalyst bed, and not all the catalyst is getting touched by the gas due to the non-ideal flow paths. So we'll escape from here and we'll go over to different model that I have open. We're going to look at this first converter. This is one of our example files that's available for folks that have ProMax 6.0. This is the kinetic Klaus bed using alumina, so every single Klaus bed here is just using alumina catalyst. This is something that you can look at on your own if you like. But what we're going to do first is we're going to look at the activity and manipulate the activity of our first bed converter. So one thing that we would like to note first is what are our temperature differences and what do our conversions look like before and after. So we haven't touched anything yet. Our activity is going to be 1. If I hover over P stream 10, the outlet, I can see that our temperature is about 593 degrees Fahrenheit. And if I go into my converter and go to the components tab, I can see conversions for some components. And specifically, I want to look at like our COS and our CS2. So our COS and CS2 have conversions of 98% and about 90% respectively right now. This is all with a activity of 1, so a fully active catalyst. So 98% and 90% conversion for our COS, CS2 at a 593 degree Fahrenheit temperature on the outlet. If I go to the parameters tab, at the bottom left is our activity cell. By default, it is 1. I'll do a pretty worst case scenario for us right now, say a 0.5, which means that 50% of our active sites are now available. As bad as we essentially would like it to go. I'll just execute the block by hitting the execute button at the top. And then once ProMax has calculated all the new conversions and reaction behavior, we'll go over to the Components tab, and we can see that our COS conversion has decreased a little bit from that 98 to 94%. Our CS2 conversion has decreased quite a bit. We're no longer seeing that 90%. We're seeing a little above 64% CS2 conversion. I'll exit out of the project viewer. I also do want to look at the PStream 10 temperature. And we'll see that our temperature has also dropped a little bit. We were at 593 and now we're at 590. We have less conversion occurring here. So we have less exothermic reaction happening. So our temperature on the outlet will decrease. This is also behavior that we could see within the plots tab of our converter. We'll go over to the converter project viewer. On the top right is a plots diagram, and we can see the temperature profile for our bed. You can also see a profile B. It'll have some more lines for us to look at, but we can also see it on a component base as well for mass flow, so we can see some increases in things like our H2O flow, and then at the bottom we have like this dark blue and sky blue line. Those are H2SO2 lines, and you can see that as they go through the converter, they do decrease, which we would expect with a Claus conversion reaction. One more thing that I want to talk about is under that parameters tab, we do have these reaction steps along with these different multipliers. So all these different reaction steps, these are all individual parameters and steps on these different reaction steps that all will contribute into the overall reactions that we see for the Klaus bed. So we do have some things like sulfur production and water absorption and hydrolysis desorptions, and formations for surface sulfate and thiosulfates that we can actually work with too. We can work with it by using the K0 multiplier or the activation energy multiplier. So essentially, whether we need more or less temperature in order to inhibit or promote reactions, as well as increasing that frequency factor on the K0 multiplier. I generally recommend that the activity of the reaction be your main tuning knob to match your Klaus bed behavior. However, if you like, you can get more specific with different things, with different reaction steps under this parameters tab. But like I said, the activity cell is the main tuning knob that you would want to use as the user. So from there, we'll go back to the PowerPoint, and you're almost done here. I've been talking for 45-ish minutes, and we're just going to summarize with talking about what we've gone over. We have a furnace that we can now model with a flame zone and a noxic zone. We have to break up that block to represent the different parts of the overall vessel. That flame zone right at the beginning, and then the anoxic zone representing the chamber of the burner. We use the flame zone Gibbs set for the combustion reaction for the flame. Again, that's Gibbs set instantaneous, and equilibrium is found. Except for that CS2 and your BTEX kinetically limited reactants that are going to be using the constraints available. The anoxic zone is where we start to get kinetic within the combustion chamber. It uses the plug flow type. There you would need to put in your chamber volumes so residence times can be determined in overall conversion. From there, the Klaus beds, you could model either the catalyst, the alumina, or the titania. Again, this is just nominal behavior for standard titanium activated aluminas. It is another plug flow type. The Klaus bed does have pressure drop correlations available for you. We modeled the ergon pressure drop correlation based off of your bed data. Klaus bed activity can also be adjusted to represent the deactivation of your catalyst. We showed that with the activity cell under the parameters tab in the Klaus block. You can put a solver on that cell to match temperature data. There are also some other reaction step pathways like your hydrolysis and your surface formations and desorptions that you can play with too. However, adjusting those to model your reaction is a perfectly legitimate way to fine-tune your model, but that activity cell, I would recommend, be the main tuning knob for you as the user. But I hope that you guys learned a lot. I hope you feel excited about using some of the new kinetic tools at your disposal for sulfur recovery units.